Hey guys, welcome back to my channel, and in today's video we are going to study stability from principles of flight. So without wasting any time, let's begin, and I hope you subscribe and like my videos because that's the most you could do since I'm making them for free. So let's begin with what exactly is stability. So the tendency of the aircraft to return to a steady state of flight without any input from the pilot after an external force acts on it is called stability. Okay, so this is the definition part. I'll explain to you what it means. So let's say you're flying straight and level over here, as you can see. Alright, look at this aircraft. And let's say due to some disturbance, your aircraft has pitched up. So if it returns back to its original state, this is called stability. That the aircraft is stable. It has returned back to its original position. So why do we need stability? So of course, when you fly, the conditions are not going to be always favorable to you. So let's say if there's some disturbing force, you need to recover from it. So you need enough stability for a uniform flight, and then you need enough stability to recover from various disturbances, and also you need stability to minimize the workload of the pilot, because if you see when it's returning back to a straight and level flight, this is not because the pilot has given any input, it's because of how the aircraft is built. So when we talk about stability, it can further be divided into two parts. All right, the first being static, and then the second one being dynamic. And when I talk about these two, the main difference between them is this is the initial stability. All right, and this is overall in general. All right, so I'll explain to you over here with an example. So let's see, this is an aircraft. All right. Oh, okay. All right, let's say this is an aircraft. So the path it's following, let's say it's like this. It's going up, it's going down, it's going up, it's going down. So if you see, when it's going up, it's also coming down, right? So it's coming back to its original state. But this is if you look at one part of your flight path. So this is called static. But if you look at the entire thing, like let's see, this is the entire path, right? It's going up, it's going down. So it's, if you see the overall part, it's not stable. So you can say it's static. When you say static stability, it's stable, but for dynamic, it's not, because static you only look at a part of it, not the entire thing. Okay, so yeah, and then static can further be divided into three. So when I talk about static, it can be divided into three again. The first being positive stability, second being neutral, and the third being negative. So let's say when the aircraft had pitched up, it returns back to its position. This is called positive. I'm sorry, this should be positive over here. It's called positive static stability. And if it continue to be like this without any change, let's say you pitched up and then it's in the same state for the entirety of your flight, then that's called neutral stability. And let's say if you, once it has pitched up, it continues to pitch up. Like there's no end to it. Now it's at this angle, then at this angle. So this is called negative stability. So there's something I wanted to remember. So for an aircraft to be statically stable, it's not necessary that it has to be dynamically stable. So as you can see here, it's statically stable, but it's not dynamically stable. But for an aircraft to be dynamically stable, it has to be statically stable. I hope it makes sense. So we'll discuss something that we did in the first chapter, the axis of the aircraft. So let's say this is your aircraft, all right, all right. So yeah, so let's say this is your aircraft, this being your elevator, this being the wing, all right. So the line from the nose to tail is called a longitudinal axis. Longitudinal axis, and then from wingtip to wingtip, it's lateral axis, and then the one that goes straight through your aircraft, it's called the vertical axis. All right. So I'll write it down. Vertical axis. But I'll just change the color for you guys. Yeah. So I'll go with blue. This is your vertical axis that's going up and down. Oh, so, yeah. All right. And now I'll, so let's talk about movements about and along this axis. So all right. So when I talk about longitudinal axis, what happens about it? Right. Oh, okay. So I'll just, yeah. So what happens about it and then along it. All right. So this is your longitudinal axis. If I keep it fixed, what happens about it? It rolls. And then let's talk about lateral. So wingtip to wingtip. I hope you remember what happens about it. Yeah, you pitch, and then you have vertical. What happens about it? You yaw. Your nose moves left and right, right? So the thing about along is when you talk about longitudinal axis, what happens along it is pitch, and what happens along lateral it's roll, and about vertical it's the same. So if you see there's an interchange over here, like in these two, when you talk about along. So this is something I want you to remember. And when I talk about longitudinal stability, I'm talking about what happens along it. So when I talk about longitudinal stability, I'm talking about pitch, not pitch. Yeah, I'm talking about when you're rolling. I'm sorry, about pitch. When I talk about longitudinal stability, we talk about what's happening along. So that's pitch. All right. So yeah, and there's something more that I want to discuss, the contributing part. So when I talk about longitudinal, so it's along, the along part is gonna be pitch, right? So and the contributing part to it is gonna be tail plane. This is your longitudinal stability. I'm gonna write S. Why? Because what helps you pitch up and down? Your horizontal stable tail plane. And when I talk about lateral stability, I'm talking about roll. So what helps you roll? Your wings, because you have your ailerons on your wings. So this is lateral S stability. And then again, yaw is the same thing, which is gonna be a rudder. All right. So yeah, and there's one more thing. When I talk about controllability, what is this? It's the ability of the aircraft to respond to controls of a displacement. So it's about how aircraft responds to control displacements. So if I'm pitching up and down, how is the aircraft responding? So the thing is, con I'm sorry, the thing is controllability and stability are inversely proportional. So if I'm too stable, it's going to be hard to control the aircraft, and if my aircraft is easily controlled, it is not going to be that stable. So let's not waste any time and let's move on to the first type of stability, which is longitudinal stability. All right. So as I told you, what longitudinal stability is, it's about the pitch axis, right? So let's say if my this is my aircraft, all right. So if I've pitched up, or just draw a simple aircraft. So if I've pitched up, and if it has a tendency to come back to a level flight, we can see its longitudinal stability. So now we are going to discuss about the factors that affect your stability. Okay. So when we talk about longitudinal stability, here I have drawn the wing of the aircraft and the elevator of the aircraft. So there's one thing I want you guys to remember: if your aircraft has nose up tendency, then that reduces your longitudinal stability. I'm gonna write launches so you guys it's shorter and you guys understand. So this reduces, and if it has, let's say, nose down tendency, then your longitudinal stability increases. All right, I hope it makes sense. So yeah, so if you see, this is the aerodynamic center and this is the CG. All right, this is the center of gravity and this is the aerodynamic center. So the thing is, if let's say this is your lift and this is also your lift, when your wing is producing lift, it's going to give you a nose up moment. But when your tail plane is giving you lift, it's going to give you a nose down limit, nose down tendency. All right. So let's say this is CG. So we can say that this arm. Okay, I'm sorry. This is an arm. All right, and this is also an arm, and then this is a force. All right. Then if we do force into displacement, we can understand what's actually happening. So if you see this part is actually giving you a destabilizing effect. This part, why? Because it's giving you nose up tendency, and this part is giving you a stabilizing effect because it's giving you nose down tendency. So the thing is, if I move my CG forward, what happens is this let's say I've moved it over here. So what's happening here is, now if it's over here, let's say this is my new CG. Now the destabilizing arm has reduced, right? and now this much is my stabilizing. So I can say when my CG moves forward, my longitudinal stability is increasing because my stabilizing arm is increasing. Same way if I move it aft, what happens? My stabilizing arm reduces. So I'm gonna write redwood. What happens? Longitudinal stability reduces. But again, when I talk about stability, if you look over here, the opposite controllability. So my over here, my controllability reduces. It's gonna be hard to control the aircraft, and over here, the same thing is gonna increase. All right. So this is what I wanted to tell you. What happens when you have forward or aft CG? So let's move to the next page and let's see some terms. All right. So here I've drawn the elevator and your wing and your center of gravity, your aerodynamic center, and all to explain something. So let's say this is. So let's wait. I just yeah. So this point over here we call it neutral point. And what exactly is neutral point? It's that point of the CG which will give you neutral longitudinal stability. Well, this is not actually good for your aircraft. The thing is, you can't fly without any safety margin for your aircraft. You need some sort of stability, right? So you can't fly your aircraft at neutral stability because it's gonna give you a neutral point because it's gonna give you neutral longitudinal stability. You need somewhat of stability, right? So which brings us to static margin. What is static margin? This the distance between your CG and your neutral point. Alright, so if your aircraft has neutral longitudinal stability, that means the CG is at your neutral point and your static margin is 0. So I'll just write it down. Your static margin, what is it? Distance between your CG and neutral point. So there's something known as minimum static margin. So what is the minimum static margin? It's the distance between your aft CG limit and your neutral point. So the thing is, if this aft limit, this means you can't have your CG behind more aft of it, right? So this part, this is gonna be from your the most aft you could go with your CG, and your neutral point is called your minimum static margin. Because if you go behind this, that's not acceptable. You need some amount of longitudinal stability for your flight. I hope it makes sense. Now let's discuss about contribution of components to longitudinal stability. So let's talk about the wing first. So when we talk about the wing, so for this we'll go up and see if your AC, when it's usually forward of your CG, it gives you a nose up tendency, which is basically a destabilizing effect. And what is destabilizing? That means nose up movement. Alright. And let's talk about your tail plane. And as we can see, that increase in lift from your tail plane gives you a stabilizing effect. Because it gives you a nose down movement. So I'll just explain how it happens. So let's say this is your aircraft, alright. So if I increase the lift more over here, what happens? It's gonna create a nose down tendency, right? But if I create more lift over here, it's gonna create a nose up tendency. I hope it makes sense because I just wanted you guys to visualize it. So now let's talk about factors that affect longitudinal stability. I just write it over here, alright. So the first one is gonna be your upwash and downwash. So let's say that So the thing is, when your upwash and downwash increases, right? This increases. What happens is this is decreasing your angle of attack. Like this is going to affect this, and your angle of attack on your tailplane reduces. Which again, if you're reducing lift over here, it's going to create a nose up tendency for the aircraft, right? Which again is destabilizing. All right, and then the next one is going to be all right. The next one is going to be longitudinal dihedral. Okay, so the thing is, okay, all right, I'll just draw it over here. This is your wing airfoil. This is your elevator. All right. So what when the designers were designing your aircraft, what they decided was that they're gonna keep your angle of incidence for your tailplane, angle of incidence for your tailplane less, and for this more, so that if so that your aircraft creates appropriate stabilizing moment. So I'll just explain to you what happens. So let's say your angle of incidence over here is 4 degrees, and here it's 2 degrees. All right. So let's say that due to some gust, this increases to 8, alright, and this increases, so 2 plus 4, how much is that? 6, alright. So from 4 to 8, that's double, right? That's 2 times. So that's like 100% increase. But 2 to 6, that's 3 thrice, right? 3 times increase. So that's a 200% increase, right? So the increase more is greater compared to this one. So this is creating, again, this is creating a nose down tendency, which increases your stability. I hope it makes sense. And then the third one being your CG position. As we know that forward CG means your stability increases because your arm increases, and aft CG your stability reduces. I hope it makes sense. And the third one is going to be power effects. Not third, yeah, it's going to be fourth one. Power effects. So let's say this is your aircraft. I'm gonna draw an aircraft here for you. Alright, and then this is your wing, this is your elevator. Alright, so let's say this is your thrust line. Alright, and this is your drag line. So when your thrust line is below your drag line, it's gonna create a nose up tendency. Alright, which again it means your stability reduces. But let's say for the same thing, this is your aircraft, your thrust line, this is your thrust line, and this is your drag line. Alright, so this is gonna create a nose down tendency, which increases your stability. And also, if you have, let's say this is your CG, and let's say this is a propeller driven aircraft. So if your propeller is located forward of the CG, alright, this also reduces your stability. Alright, so I hope it makes sense. And let's talk about the fifth factor, being flaps. So what happens when you deploy flaps is it increases the downwash at the tail. So the downwash increases, and what does this do? It reduces your dynamic pressure at the tail. Alright, so not only it's increasing your downwash, but it's also reducing your dynamic pressure at the tail. So these both, this plus this, it has a destabilizing effect, because this is going to create a nose up tendency. When so what happens when your downwash increasing, your angle of attack reduces on your tail plane. I hope it makes sense. Alright, so let's move on to the next type of stability, which is going to be lateral stability. Alright, so when I talk about lateral stability, it's about the longitudinal axis. This is the first thing I wanted to remember. The second thing, that it's about rolling. Third, the contributing factor. What is going to be the contributing factor? It's the wings, because you have ailerons due to which the aircraft rolls, and ailerons are around the wings. So yeah, so let's say this is your, I'm going to draw the back part of the aircraft. Let's say this is your aircraft. All right, so let's say, so due to some reason it has rolled somewhat like this. So if it has a tendency to come back to this state, it has lateral stability. All right, this is the back part of the aircraft. I hope you guys understand. And let's talk about the factors that will affect your lateral stability. All right, so the first let's talk about low wing aircrafts. So what a low wing aircraft is? So let's say this is your aircraft. All right. So if you have wings, I'm sorry, if you have wings that are mounted low over here, then it's called a low wing aircraft. And then you have aircraft that have the wings high up here. All right. So these are called high wing aircrafts. So we're going to discuss about low wing aircraft. So let's say there's this low wing aircraft that has rolled to the right due to some external factor. All right. So I'm gonna. All right. So let's see what happens now. Let's see. This is your relative airflow. That's so. Your in this case, your aircraft has your right wing low and your left wing up. All right. So let's say this there's this airflow that's coming. So yeah, now I hope you guys remember what relative airflow is. So when let's say this is your relative airflow that's coming. All right. So due to this wing being low and this being high, what happens is your angle of attack is further reduced on this part, your right wing, and on your left wing, what happens due to the low wing, your angle of attack is increased over here. All right. So due to this, if the angle of attack is increased, it will go up even further, and since it's reduced, it won't go that up. So this there's gonna be the aircraft is gonna roll even more to the right, right? And again, if it's not coming back to its original state, it's called destabilizing. So this is due to your low wing, your lateral stability reduces. So for the high wing, it's gonna be very much opposite. For your high wing, your stability is gonna increase. All right. So the next factor is gonna be dihedral. All right. So what is dihedral? I hope you remember your wing, when the tip of the wing is above your root of the wing, right? That's called dihedral. So let's say the same example, but this time, if I have low wings, I have some dihedral. All right. So let's say it is this my aircraft now. It has rolled to the right. All right. So now it has rolled to the right. So when I talk about a dihedral wing, the thing is it's not affected by the airflow beneath your wing. So let's say this is your airflow beneath the wing. All right. So this is not really affecting your angle of attack. All right. It's more likely it's mostly affected. I just rub it off by the airflow that's above your wing. So let's say this is your airflow. Let's say this is somewhat your airflow. Sorry for my drawing. All right. Due to this, so what happens? Your angle of attack on your the wing, the downgoing wing is more, and here it's less. So what's happening? It's creating a rolling movement that's bringing it back to its level right, which is this. I hope it makes sense. And then the same thing, the opposite thing is gonna be for anhedral. I hope you guys remember what anhedral is. When your tip is below your root. So let's say this is the aircraft. This is some type of, if your aircraft has wings like this, then your stability is gonna reduce. Your lateral stability to be precise, and here it's gonna increase. All right. So the thing is, if you have, let's move here. So high wing. I'm sorry. I just yeah. So high wing, your stability increases. Low wing, your stability reduces. Anhedral, your stability increases. And then dihedral, again your stability reduces. All right. So here I'm talking about lateral stability. Keep that in mind. So the thing is, if I'm using my low wing aircraft, which is creating less stability, I have to pair it with the anhedral, right? I'm sorry. This the I need to correct this. This is wrong. Correction. So your dihedral increases your stability, not your anhedral. And then you have your anhedral here. All right. So if I'm really sorry for this, so if my low wing Alright, yeah. So if my low wing is reducing my stability, I have to pair it with something that increases it, right? So for that case, I have my anhedral wing and my high wing. So there's too much stability, I have to reduce it somehow. Too much stability is not good because it's going to reduce the controllability. So for that, I have my anhedral. So what if I pair my high wing with my, I'm sorry, I wrote dihedral over here, dihedral. So if I pair my high wing with dihedral, the stability is going to be too much that it's going to be very hard to control the aircraft, in fact. So that's why we don't do it. I hope this small concept makes sense to you. So the next characteristic is going to be sweepback. So I hope you guys know what sweepback actually is. So let's say you are on a right side slip. So let's say this is your relative airflow. Alright, so opposite to your flight path. So I'm gonna write it down. So what happened here? The wing, which is into the wind. In this case, this is it's gonna be this one. It's more. What the hell? Yeah. So this is wing into the wind. What happens? This wing has more lift, right? So your relative airflow is on this wing is increasing, so definitely your lift is gonna increase. Comparatively, your left wing has less lift, right? So this is gonna generate a stabilizing movement to your left, to the left, alright, and it will bring back to your original flight path. So sweep back again has positive stability because it increasing, it's gonna increase the stability, alright. So let's talk about the fin. What is the fin? It's the vertical tail plane where you have your rudders. So the next part is gonna be fin. So over here, since your fin is above your center of gravity, so this is going to increase your stability to some extent. Alright, so the next part is going to be flaps. What happens with flaps? So let's say uh, this is my aircraft. Alright, this is my CP. Alright, center, and this is my CG, and this is my CP. Alright, so what happens when I deploy flaps? What happens? So my CP is going to move inward since it travels from where the lift is being generated. So it's gonna, let's say this is the new position. So what happens if this was the previous movement, the arm, all right? So the arm is reduced. So now the distance between your CP and your CD has reduced. So this reduces your stability in turn. So the next stability is gonna be your directional stability, which is gonna be along your vertical axis, and your main contributing factor for this one is gonna be your fin. All right. So what happens, let's say this is your aircraft. This again is the top view. Let's say it yaws to the right, and if it has a tendency to come back to this level flight, then we can see it has directional stability. And this fin here is what helps it achieve it. So so it's quite common. Let's say this is the back of your aircraft. Alright. So it's quite common that some aircraft manufacturers, you increase the size of the fin by adding a dorsal over here and a ventral over here. So this indirectly is increasing the size of your fin. So what happens is your dorsal. So this is dorsal, and this is your ventral. All right. So dorsal plus ventral increase your stability, your directional stability. All right. So what the thing is, so this is your CG, center of gravity. Since this part dorsal is above your CG, so dorsal will also increase your lateral stability. But since ventral is below CG, it reduces your lateral stability. Alright, I hope it makes sense. And so let's say this is your aircraft, alright, alright, and let's say that this somewhat here is your CG. So the more mass you have after CG, your directional stability increases. So that's why you add your dorsal and ventral. And the same way how you have the more mass you have below CG, your lateral reduces. So that's the reason why that happens. And let's jump on to the next topic, which is going to be. So the next one is swept back. So yes, swept back also gives you a very small stabilizing movement, so it also increases your directional stability, but very less compared to the others. So yeah, so one more thing I wanted to tell you guys. So the surface behind CG is called keel surface. All right. So if you increase the keel surface, your directional stability increases. So just keep in mind, surface behind CG is keel surface. All right. So now there's something I want you guys to know. So I wanted to discuss the Dutch roll with you guys. So what exactly is Dutch roll? It's out of phase turns. What do I mean by out of phase? So let's say if you roll to the right, and then because of your out of phase turns, it's gonna create a yaw to the left, and similarly when you yaw to the right, it's gonna create a roll to the left. So these are called out of phase turns. And why does this happen? This happens when your lateral stability is too much, but your directional stability is too less. So this can cause Dutch roll. So how can we fix this? So you can see over here, by the way. So this is how a Dutch roll happens. So to fix this, we have a yaw damper. All right. So what does this do? It displaces the rudder proportional to the rate of yaw to dampen out the oscillation. So it's basically damping out the oscillations to reduce your out of phase turns. So for example, when you're rolling to the right, it's creating a yaw to the left, right? So it will dampen it out. And let's say if this fails in flight, then you're not supposed to use rudders. You're only supposed to use roll inputs, which are your ailerons. Because if you use rudder, this may lead to loss of control. Alright. And then similarly, we have something known as spiral divergence. So what exactly is spiral divergence? This is quite opposite to Dutch roll. This happens when your directional stability is too much compared to your lateral stability. Alright. So there's one important topic I want to explain you guys. So when I talk about dynamic stability, let's say this is how my aircraft path looks like. So if there's no, if it, so first of all, if you can see over here, if it's going down, the aircraft it's also coming up. So yeah, it's going to be statically stable. But if you see overall, as I told you in the start, dynamic is about your overall path of the flight. So if you see overall, it's not stable, right? It's going up and down. And if you see the frequency is neither increasing, neither decreasing. So this is neutral. And let's say if the frequency reduces with time, let's say this is the path, then this is called positive. And if the frequency increases, so let's say it started like this or going like this, and this is called negative. All right. So to reduce this, we have something called aerodynamic damping. What does this exactly do? It decreases the oscillation. So this is how you fix your dynamic instability. So there are a few factors depends on your altitude. So if your altitude increases, what happens to your density? Your density reduces. So air is becoming thinner. So due to this, your aerodynamic damping reduces. So the damping is going to reduce. So the next we have airspeed. So if your airspeed increases, your parasite drag increases. Right? I hope you guys remember. So due to this, again in turn, the damping increases. Alright, so we have finished this chapter. So I have not covered all the topics. I've covered topics that are important for your airline and also for your Dgca exam. There was a lot of topics that were not really important for you. So I hope you guys study this well. And yeah, please solve Oxford for all the chapters. And if you have any doubt, then please comment down in the comment section. I'll reply to you. Alright, have a good one.